When it comes to new developments in electronic components, in many cases, it's taking a component that operated well but had some kind of a limitation. And the engineers would look at it and say, "Well, I wonder what we could do to this to improve it." And somehow, then somebody come up with an idea and say, "Well, why don't we combine this component with this component and see if we can do something like that?" And in many cases, that's what happens. That's the way the new component sort of comes to be. Um, a fairly famous businessman at one point said, "There's no money in inventions; it's all in improvements." And to some degree, that's really true. Let me give you a few examples of the combination uh, components that we already use all the time. And I'm just going to give you an idea of some of the things that have been put together. One of them, to begin with, is really just taking a simple diode. And we know that the diode usually has a very low forward barrier voltage. And a good diode has a really high reverse blocking diode if it's in good condition. And at some point, they discovered that some of the diodes actually conducted just fine, but they had quite a low reverse blocking voltage. So they started looking at that and they said, if we were to dope this particular diode in a very specific way so that we could make its reverse breakover voltage kind of predictable, this could be a pretty useful component. And that's where the Zener diode came from. So the Zener is really just an improvement that occurred when looking at the just looking at the regular diode. Okay, so the Zener is just an improvement, and it comes in the manufacturing process, in the doping actually. Another one is the transistor. We think of this as being the transistor. Like this: base, collector, emitter. I'll make this one an NPN. But whenever you see a transistor, it's really just a combination of two diodes. And you can take this same transistor, and what you realize is this was really just this. And this is the emitter. See that we're not pointing in. And what most people, you don't really ever think of it. You could actually draw the same. You could draw the same arrow on here. We don't, because that's how you can tell which one is the emitter. But in any case, really, this is what a transistor is. Okay, it's two inverse series connected diodes. Okay, so a couple of components combined to make a transistor. Another one that we've already talked about, and it's the SCR. So the SCR is, quite simply put, combination of two transistors, and those transistors are a PNP and an NPN. And this N becomes the cathode of the SCR. This N becomes the anode, and the gate attaches here on that inner P layer. So there you have another combination. This one, the SCR, really just a combination of two BJTs. Okay. While we're talking about the diac, let's take a look at this one. we've said that the diac is an electronic component, very, very small. It's used in AC. It will conduct either direction, but it has to reach its breakover voltage in order to do that. Now, what other component did we talk about that had a breakover voltage? And if you recall, it's the Zener. So what happens is if we take this Zener and we connect it in series with this Zener that is biased opposite that, there's those two Zeners, we connect them together like this, and we come out here, these two terminals, we could call MT1 and MT2, and this would be a diac. That's a diac right there. And so another combination of components that makes something new that operates in a very unique way. These, of course, used for trigger devices in the thyristors. There's another one that we also talked about, and this is actually interesting because this is a recombination of a combination. And so if we take an SCR with its cathode and its anode, then we take another SCR with its anode over here and its cathode over here. Here we have two items. Each one of them is a recombination of two transistors. We're going to take them and hook them up like this. And now, what do we have? Well, essentially, this is a triac, right? We put one gate on there, and we have a triac. It now becomes an AC component for phase control in an AC system. So another interesting combination that, we took something that we had, combined it in an interesting way, and came up with a completely new purpose for it. And so in many cases, this is how the things improve and how we come up with new components that are really useful for us in the in the electronics that we're working on. There are many, many different variations of the transistor, and it's been approximately 75 or 80 years since the first transistors were started to be used, and but like so many other things, with all of the changes and advances in technology, many different types of transistors have been designed, and they widely fall into a couple of categories. And so we have BJTs, which are these are a current control. They're a current control component. And we also have the FET type of transistors, and these are controlled by voltage. Now, BJT, of course, refers to bipolar junction transistor, and the FET is the field effect transistor. And now, when it comes to the FETs, there are they're broken down again, and the one we're going to be looking at in a little bit of detail, I want to show you how it works, is the MOSFET, and we've already spent some time on the BJT. So what I want to do is I just want to give you a little bit of an idea how the FET works, and but just in broad strokes here, I want to show you some of the advantages of the BJT, and what we're saying is this is as compared to each other, okay? So these ones we know come in NPN or PNP. And when it comes to FETs, they come in, it's categorized a little differently. They call it N channel, or P channel. And I'm going to give you a little bit of a description of what that channel is about. Now, when we say that the BJT is current controlled, what we mean is that the thing that actually causes collector current to flow in and back out, and this is essentially our main current path, is C to E. The thing that causes that to happen is actually the input of base current, and this current becomes part of this emitter current. In other words, this is literally two currents becoming one. And we've talked about the current relationships where I of E is I of C plus I of B. So we know this is electrically, there's electrical continuity between the base and the emitter. And it's the size of this base current, which is the controlling current. Okay, so this is the control current, okay? Controlling current right there, and it controls the collector to emitter current. Now, just to show you what happens over here on a FET, what you have is essentially they're termed slightly differently, and we would say source and drain. Okay, source and drain, and what we have at the input is a gate. Okay, so we have a gate and a source and a drain. And something interesting though with the field effect transistors is that you need to realize is that there's actually no current. There's no current flow at this point. Okay, it's called a high impedance connection here. So what happens is it's actually just the presence of voltage at this point that causes an effect of constricting or opening the channel. And it's literally the presence of voltage that does that. And so, depending on the configuration, either like a lower voltage will cause a higher current to flow through, or in some cases, it's a higher voltage applied to the gate that will allow current to increase and flow through the source to drain. But it's all done with voltage, okay? Now, typically speaking, BJTs compared between the two, these ones handle larger currents, okay? So the load current can be greater. When it comes to the FETs, the current is less, but the thing that they do is that they switch rapidly. Okay, so they switch faster, and in particularly, it's the shut off. Okay, they shut off, especially more responsively, for sure, than the BJT. So that gives you an idea of just got a little bit of a comparison, and we're going to go ahead and I'm going to show you a little bit more about the FET and how it works. So I've drawn a MOSFET here, and a MOSFET is probably one of the more common FET transistors. This stands for metal oxide semiconductor field effect transistor. That's a bit, isn't it? Okay, metal oxide semiconductor field effect transistor. And as I mentioned earlier, the interesting thing about this is that this transistor, like most, is set up, of course, as a switch. In other words, what we want to do is we want to have a load current that's going through it, and we want to be able to switch it on and off and control it. And so the way that this one is controlled is by applying voltage to the gate and also to the substrate, which is kind of the bulk of the component. And so these two lines would be tied together. The gate and the substrate would have the same potential applied to them. And so what it actually does is it creates it creates an effect where what you're going to do is it's kind of like a squeezing effect, and it creates a situation where there will be actually a lot of electrons in this area here. In here. And so what happens is when there's a lot of electrons in this area, then this becomes from here to here, this area right here, which I'm going to show you right here, this is the channel. This is what we call a channel. And so, if there's more electrons in that area, then current is able to flow really nicely through there. And when you remove the voltage from these points, then these electrons spread out into this material a little bit, and it kind of shuts off. All right. Now these come in N channel and P channel, and so the exact workings of what goes on in here, of course, get pretty complicated. But in general terms, the idea is that the voltage that is applied to the gate and to the substrate is going to, in one way or another, it's going to control the load current that flows between the source and the drain. And it's going to do that, and there's no actual current flowing into the gate. All it is you're applying voltage, and it's an electrostatic effect that creates the channel, and either, as we would say, it either makes the channel better so that it can flow, or we do have actually also a model that kind of tears down or reduces the channel that's actually there, and we call that depletion. And if we make this channel better, like if it's basically off, it's not conducting, and we apply voltage, and all of a sudden this channel improves, we call that enhancement mode. And so I'm going to show you just now how you would see these in a different circuit. And so let me draw these up for you, and then we can talk about that. Now, these two circuits that I've drawn for you, these represent, this is the best way to describe the difference between a depletion and an enhancement mode MOSFET. So let me show it to you like this. Now, in this first case, the sort of the key place where we want to look at it in terms of remembering this is, let's look at these symbols over here. And you're going to notice that this line right here in the symbol, you can think of that as the channel, okay? And in this one here, that channel is actually complete, even though I haven't applied any voltage to the circuit yet. So this is open, but this channel is complete. Now you can see that I've intentionally left my gates. They're not connected. There's no voltage being applied to the gates, and let's see what happens. So to begin with, we're going to close this switch. So I'm going to put that, and we're going to close the switch. Now in this one, current will immediately start to flow. There will be current flow. And it will be flowing pretty much at its full rate. In other words, the conductivity between the source and the drain is right now at its maximum capability. Now, what happens is if I apply some gate voltage, which is abbreviated like that. So if we apply some voltage to the gate, what happens is it starts to produce an effect, and it's actually a squeezing effect, and it basically squeezes off. So the field that develops is actually like a constricting field, and it squeezes off the channel. And so as we apply higher and higher levels of voltage to the gate, remember there's no current flowing in, it's just a field effect of constriction, and this current goes down to 0, okay? So that is with the application of that voltage. So when we get up to our rated gate voltage, then our current will have hit 0. Now remember, this will modulate between 0 and full current, okay? And that will basically be depending on how high the level of voltage is applied at the gate. So remember, with no voltage applied, full current will flow through. And so what we say is in this one here, this is called depletion. And the reason that it's, I guess, you know, the word deplete means to take away or kind of decimate or get rid of something, right? Depletion. You know, it's a word basically like we depleted our supplies. Everything's gone, okay? So think of it as you have a channel and you deplete that channel. So in other words, you're wiping it out. So you deplete the channel, and at the end, you don't actually have a channel, and so you have no current. Now, the inverse of that is shown in this one, and this is called enhancement. Enhancement mode. And so what happens here is that when we close the switch, we apply voltage from our source to the source here, and we've got our load hooked up to the drain so it flows through. But in the absence of a voltage at the gate, you see how this channel is broken? And say, well, you know what? It's actually not complete, and it's not good enough. That channel is not good enough to pass current, so it doesn't pass any current. So what we have to do to this channel in order to get it to conduct current is we have to enhance it by adding some gate voltage. And what the gate voltage does then is it basically puts an electrostatic force on, you know, the holes and the electrons that are in the substrate and in there, and it actually improves the channel and it makes the channel so that it will work properly. Now, important thing to note is that, so that's when we add gate voltage here, we're actually going to have, so as we add this VGS, now we're going to have our current is going to come in and we're going to have current flowing. So when we have current here, we're going to have current here. Now, let me just finish this off. You'll notice both of these symbols have the arrow pointing in, and what that indicates is that in both cases, both of these are actually N channel. Now the only difference, of course, with the P channel is just the polarity of your connections. Okay, these are both N channel, which is the same as the, you know, it's the drawing that I just gave you before was an N channel MOSFET. And so what we really would look at then, this would be called simply a MOSFET. And this would be called an E MOSFET. So the enhancement MOSFET is just, they stick an E in front of it. This is an E MOSFET, and this is a MOSFET. And so with this one, it's just the inverse. It's a little bit like a normally open or a normally closed switch, with the exception that in this case, you know, with switches, when we energize, they instantly close, or if it's normally closed, it instantly opens. With these one, it's a modulated effect. So in other words, here we start with full current. As we raise the gate voltage, the current will slowly, in a modular way, it will reduce down. And the same here, we're going to start off with no current, and as we add gate voltage, the current is going to go from 0 up to full current from source to drain when we have our full voltage applied at the gate. Remember, no current flowing into that gate, just a voltage field that's affecting the channel. All right, now this is starting to look a lot like the quiz that I gave you earlier on, and this has to do with the symbols. And so what we want to do is just go through this and make sure that we're aware of which one is which. So the one that's just labeled MOSFET is the depletion type, and so you can see there's your channel. It's in, it's already connected, and you have to actually deplete that to shut it off in both of these cases, N and P. So these are your depletion ones here. And then down here, you actually don't have a channel, and you can see it's broken line. And so you actually have to enhance this channel. So it's called the E MOSFET. But in terms of the leads, we have the gate here, and we have the source here, and we have the drain here. And in some cases, it depends a little bit on manufacturer and just what the application is. Sometimes this substrate lead can actually be a lead, or it can be internally connected, because it actually has to be connected in such a way that it has a similar potential. Even though there's no current flow between them, you need that potential in the substrate to create the effect of either being able to sort of put some pressure that either makes a channel or put some pressure that constricts and cuts the channel off. So in either case, so those are the symbols that we use. Now, now that we've had a little bit of exposure to the field effect transistor, a little bit of an idea how that works. We know that that the advantage of a field effect transistor to a BJT transistor is that this one, because of its high gate impedance and the fact that in order to turn it on and off, there's no actual gate current that has to start and stop. It's just a voltage that is applied or removed, so that field just builds up, or the field bleeds down. Now that happens much faster than in the case of where you have a base current that actually has to flow and then has to stop, okay? Because current is harder to stop. And so the field effect transistor has very, very quick response times in terms of turn on and especially in terms of turn off. And so that's a huge advantage that we want to be able to harness. And when it comes to the BJT, that type of transistor, of course, a very low voltage drop from C to E. And so in the cases where you have a lot of current flowing in a BJT transistor, um, it's a real advantage having a very, very low voltage drop across that junction. And so one of the advantages, of course, of the BJT is that lots of current capability. And so what we need to do now is figure out a way to put these components together. And so I'm going to do a little work on the board, and then I'm going to show you what I've got. Okay, let's take a look at what I've drawn. So what we have here is essentially now the IGBT, which is insulated gate bipolar transistor, is essentially a MOSFET plus a BJT. And the interesting thing is that what this device does, the IGBT, is it really puts together the best of these two components in one component. And so this has become a very, very heavily relied on component particularly in high and very high power applications, okay? So let's take a look. Here I have an N-channel E MOSFET. And so we know that the current direction would be that the source current would flow into the source, and we have to apply some gate voltage to enhance this channel so that that can flow. So when we apply gate voltage here, we allow current to flow through the channel and out the drain. Now let's move over to the far side. Over here, what we have is a is a BJT transistor. Now we actually use a PNP, and remember, in an NPN, the collector current plus the base current equals the emitter current. But in a PNP, the currents flow a little differently. So you can see the current comes in the emitter, flows in to that center junction. Some of it splits off and goes out the base, and the rest of it goes out the collector. So actually, in a PNP, the um, the uh, the emitter current is still the combination of the base and the collector currents, but the currents just flow in a different direction. So you can see that here the current will be flowing out of the base lead. Now here's what they've done with this one. They've taken this component, which is the enhancement N-channel MOSFET, and they've connected the base. Now remember, the current is flowing out of the base of this transistor. So it comes in here on this terminal, flows out of the base, and when we apply a gate voltage here, it will allow that current to flow through, which means that this switch here from E to C will actually become made, and the main current will flow through. The interesting thing is that this on and off of this channel, extremely responsive and fast, whereas this current here by itself has a hard time making and breaking, so it's very slow. This one, because it's voltage controlled, extremely fast, and so it opens and closes because of this current opening and closing because of the voltage control. Now it opens and closes the main current contact very quickly, and most importantly, it opens it very quickly. And so this device, the IGBT, has it's considered to have high current interrupting ability, so it can switch large amounts of current, and it can do it really reliably and very, very quickly. And so this component, particularly very interesting in the process of inverting, so taking DC and creating different types of waveforms, and particularly pulse width modulation, which we're going to talk about in just a few moments. Okay, so next I'm just going to show you the symbol for this, and then we'll carry on. So there's the symbol. As you can see, even the symbol is a combination. We've included the gate designation that we would have used for the MOSFET. So the gate, and but our our throughput terminals, rather than being source and drain, are actually collector and emitter. So you can see it's really very much a combination. And just looking at the symbol, there's a few things you can tell. Right here, you can see that there's that that insulation space, or you can see it's not connected. There's no actual conduction between the gate and the semiconductor material. Insulated gate. Remember, it's a sulfur dioxide insulation. They actually collect glass. It's a very brittle sort of an insulating layer. Okay, and load current flowing, of course, through between collector and emitter, and voltage here just controlling it. And so just to summarize this IGBT, this component considered as high efficiency. And really, if you think about it, high efficiency, there's a couple of reasons for that. First of all, low C to E voltage drop. So, and that's like the BJT. So because that's very, very low, when load current is flowing, you're not developing a whole bunch of heat there, okay? The other thing is no current here. So, no heat losses from current flowing through. And one of the things that in a BJT transistor that definitely causes some heating problems is that the base current flowing in. and combining with the emitter current. That where that base current flows in, there's a lot of heat generated there. So that's one of the inefficiencies of a BJT. So high efficiency here, 0 amps on the gate, and low voltage. Another huge advantage of this, we already talked about this, is the rapid switching. One more interesting characteristic of the MOSFET itself, and part of that characteristic is even built into this IGBT, is that a MOSFET is the opposite of a BJT when it comes to its temperature coefficient, whereas a BJT tends to become more conductive with a rise in temperature, and we call that a positive temperature coefficient. The MOSFET is actually the opposite, and so it tends to self-regulate a little bit, and so part of that even helps a little bit with the design of this component. And the final point that we would like to make about this one, and really significant, especially when it comes to its applications, is high current capacity. High current. And so these are used particularly for the control, the main current control of large motors, induction heaters, all sorts of high to very high current loads can be controlled with IGBTs. All right. So the current, when we say high current, typically, as long as we're talking similar sizes, this IGBT is between 2 to 3 times the current of just of a MOSFET. And so we've achieved that by incorporating the characteristics of the BJT, and so that it actually handles a lot more current, but we've got that nice fast switching which came from the MOSFET. All right, let's take a look and see what we can do with these IGBTs. Now, this is really interesting. Many applications, but one of the important ones is in the VFD. Okay, so just in general terms, if you look at a variable frequency drive, essentially many different designs out there, but their key elements are this. You're going to have a processor that's going to control everything that happens here, and you'll have some AC input. Normally, it can be single phase or 3-phase. Your first section that you come into is a rectifier, and so it's going to take your AC voltage and it's going to rectify it normally with a bridge type rectifier, and get all of your ripples on one side. In the next section, okay, so the DC bus is going to run through all the way through this thing. And in this area, what we call the filter section, now we're going to start taking and filling in, with some capacitors, some inductors, and doing a few things to get this cleaned up to a straighter line. So by the time we pass it into the inverter or oscillator output section, we should have a nice, clean, flat, straight line DC. And not only that, we can actually take that output and we can set it up, with a midpoint, what we'll say is 0 volts, positive volts, and negative volts. And that means that we can output a voltage that goes from 0 to a positive peak value, or from 0 to a negative peak value. And so lots and lots of options. Now, when it comes to the output really of this thing, the main thing that we can do is as we output, now remember we have, in this unit, we would have 6 IGBTs, 2 per phase, one to handle positive pulses in this side, and one to handle negative pulses in this side. Now, this diagram that I can do for you here only represents one phase, okay? So this would be 2 IGBTs. This one would be doing the positive, and this one would be doing the negative. And remember, whatever I show you here is also happening in 2 other phases, 120 degrees apart. And that, of course, is controlled by the processor. All right. Now, let's take a look what we can do. Well, if we can change the frequency, and we do that by the speed at which we give positive pulses and then negative pulses, then we can actually we can adjust, essentially our speed, right? Because frequency and the number of poles are what determine the speed of the motor. So if we slow the frequency down, then our sync speed will go down and our motor speed will go down. And our current will be, of course, controlled by the speed and the voltage and all those factors. The other thing that we can control perfectly is how high is this positive pulse and how low is this negative pulse of voltage. And so by raising or lowering the size of those voltages, we can actually determine what the voltage output will be. And one of the important things, and this is beyond the subject that we're looking at right now, but in motor controls, so you're looking at the you'll be looking at the electronic speed drives, and you'll realize that volts per hertz, very, very important factor. So let's take a look at how this would work. This is called really pulse width modulation. And here's what happens. So we have this voltage, this DC voltage available, and I'm just trying to give you the idea here, okay? It's hard to show you in a lot of detail, but let's look at it like this. Let's say that I started by giving a pulse of voltage that looked kind of like this. And this amount of time is actually kind of important. So how long that pulse is for. So in other words, I can make this longer. I can leave that voltage on for a longer period of time. And this is called duration. That's the duration of the pulse. And then the IGBT, bang, shuts off. Then the controller or the processor waits a little bit of time. It's being, of course, controlled by an electronic circuit, probably an oscillator circuit, and it waits a little while, and then it turns the IGBT on again. Okay, but this time maybe for a shorter amount of time. So it determines not only what the duration is, but also this is called the interval. Okay, so it can control both the interval, that's how far it is between pulses, and it can control the duration, which is how long the pulse is. And the other thing that we just mentioned is it can also control how high the voltage is. So tons of control over this thing. So just imagine a situation like this where we put in some pulses. I'm not going to try and draw them completely accurately, but what I want you to see is this. If I gave a bunch of positive pulses like this, and then I switched to doing negative pulses like this, these are just voltage spikes, okay? They're just voltage spikes. And depending on the duration and the interval, this will produce something that looks like this. And we will get a current waveform as a result of those voltage spikes, depending on their duration and their interval, and we can produce a waveform like that. Now, the interesting thing is that we can perfectly control the amount of time. So if we do all of these pulses and all of these pulses in 16.67 milliseconds, then we have 60 hertz for our motor. And but what would happen, I guess, is what's that times 2? That's going to be 33. I see 16 is 32. 33.3, something like that. if we extended this time out to around 33.3 milliseconds, then what would happen? Well, I'd have to draw it longer, but without drawing it longer, if I just said this amount of time is 33.3 milliseconds, then you did the math on it, you'd find that this would be 30 hertz. And that's exactly what we do. They can, the processor can determine the speed at which the impulses are put out. And so if the impulses are put out at a slower speed, it's going to drag out over a longer time. It's going to result in a lower frequency for the motor that's being driven by that power source. And one of the interesting things that happens is, as you well know, the reactive inductance portion, the reactance of a motor, is determined by the frequency. So what would happen if we continued supplying the exact same line voltage to the motor, but we reduced its reactance to half? So in other words, if we go from 60 hertz to 30 hertz on a motor, the reactance will reduce to half. And so what would happen is that our impedance would be pretty close to half of what it was. And that means that at the same voltage, our current would start to rise. And so we'd start to have real problems with the motor. So there's this principle, and it's this: as long as we maintain the same volts per hertz, then everything should operate pretty well. So if you're going to operate this motor at 30 hertz, that's going to give you, instead of running at, say, 700 RPM, now it's going to run at 350 RPM, as long as you take care of one thing. And you have to make sure the volts per hertz are the same. Now, nothing could be easier in this drive than doing this, because all you have to do is this. You reduce the overall voltage of the spikes. And now at 30 hertz, we redraw our current line and it looks like this. Okay, so instead of being fairly tall like it was before, now it's down here. Okay, so we stretched it out first to make it 30 hertz, and then we cut down the overall voltage of the pulses so that our volts per hertz are still the same. So half the frequency, half the voltage, the motor runs perfectly. Okay, so that's the idea of pulse width modulation. And obviously it's more technical than that, but this is a little bit of an introduction. And what is it that's making these pulses to be able to be switched on rapidly in the positive or the negative direction? Well, it's this amazing little component called the IGBT. In conclusion with the IGBT, I would like you to make sure you take a look in the handout section. And you're going to find a few problems in there that I'll walk you through it, and I'll show you the specific patterns, some of the patterns of the pulse width modulation, and just a couple of problems to work through to make sure you understand about the volts per hertz, and how those changes in the inverter output actually affect the motor. Okay, so just a little bit of stuff there to work through. Now, what I'm going to do is I'm going to take away this, and I'm going to introduce you to the last thing that we need to cover in this section, and it's something called ESD. And what this stands for is electrostatic damage. Now, electrostatic is essentially just saying, lightning, but on a smaller scale. So this is charge that builds up from friction between two bodies of material. And when it finds a place to discharge, it does it. And that discharge creates, um, some type of a flash. In lightning, of course, really, really impressive. You're talking about, currents in the hundreds of thousands, perhaps millions of amps. Amazing amounts of current and charge that transfer there. But you'd be surprised what the voltage of static electricity that may make actually a little bit of a discharge that you may almost not feel, definitely not see or hear, and it can still be enough to literally destroy an electronic component. So we want to talk about electrostatic damage to electronic components. Um, I do want to put in a little advertisement right now. You will find a document that I've placed in the handouts, and I'd like you to take a careful read of it. But I am just going to highlight some of the key points from that, and we want to see, just talk about this a little bit. So just to give you the highlights, many of the current electronic components are particularly susceptible, so easily damaged or destroyed by ESD. And in fact, a couple of the most sensitive ones are something called VMOS and the MOSFET. Extremely delicate in terms of being damaged by ESD. And one of the real weak points with the MOSFET is it's that sulfur dioxide glass layer of insulation. It's like a controlled oxide that builds up, that they produce it. It's this little film on the semiconductor, and then of course they fuse onto that the gate lead. And but what happens is a little bit of an electrostatic discharge actually tends to crack or at least break the edges of that insulation, and then it makes it quite easy for short circuits to occur in the component, and then of course your whole circuit operation deteriorates. So it's quite interesting to note that you can actually have damage or destruction even as low levels as low as 30 volts and like 1 milliamp. And I'm just I'm just looking at this word, and I think it's a cross. This is a hybrid word that I just invented. This is a cross between destroyed and destruction. So you might want to make a note of that one. It'll be everywhere pretty soon, all right? Now, one of the cruel things about it is that when you have an electrostatic event, as they call it, okay, so something happens that shouldn't happen, and a little zap of electricity goes into a component. Here's the trouble. In about 10% of ESD events actually destroy the component, okay? It's done. So what happens to the other 90%? Well, here's the problem. The other 90% do what they call latent damage. And the problem with latent damage, this is really just sort of a term that means it's just kind of some damage that's stored in there, just waiting to come out, waiting to happen, waiting to raise havoc. And so what happens is in about 90% of the cases, what happens is the component is compromised, but in routine testing before, like say you were building TVs, you would test it and it would pass. But the truth is that the component, there's some components in there that have been heavily compromised in terms of how well they perform. And they could cause, first of all, intermittent problems, and then early failure. Okay, so yeah, intermittent problems, which for any of you that have ever had an intermittent electronic problem, you know how annoying it is. So intermittent or just straight up early failure. Early failure. And so it's the sort of thing that in terms of if you're a company that's building different pieces of equipment, this is the kind of thing that can sink you pretty fast, because especially if you provide a warranty, because if you have components that have been assembled in a place where there were not strict protocols around how the components were handled during the manufacturing process, you can buy something that looks good, comes in a nice box, but it's actually pretty much inferior and could fail really, really quickly. And so some of the procedures around maintaining the quality of the components and preventing electrostatic damage, there's some very specific points, and I'm going to outline them for you here in just a moment. But before I do that, what I want to show you is, now we said that voltages as low as 30 volts can damage or even destroy electronic components. And so one of the questions that comes to mind is, if I'm working in an environment around electronic components, what do I have to do to sort of develop enough static on me? Like what level of voltage do I really build up just from static in the air, static on a coffee cup, static on paper, static on some plastic wrapping? Okay, how much static voltage can I develop? And there's a chart included that I want you to take a look at and read, but you're going to see there that you can easily build up between 400 and 35,000 volts of electrostatic charge. Electrostatic charge. Now, 35,000 volts is going to produce one of those zippers, sort of shocks that if you touch something, you're probably going to actually see the arc, feel it. Not necessarily painful because the current is very low, but this one here, not much chance for the electronic components involved. Okay, so 400 to 35,000 volts, typical in normal workplaces. Some of the factors, of course, that play into how much voltage you build up, it has to do with, of course, what the materials are that are in contact with each other, and also the humidity and temperature play in as well. But plenty of opportunity for damaging voltage levels. And so handling is really going to be one of the important factors. Now, just in terms of voltage thresholds, in terms of whether it, we said that 10% are destroyed, the other 90% are damaged. And one of the interesting things about it is, if you have an ESD, event, and in terms of the amount of voltage, like let's say that a component is sensitive to 100 volts, okay? 100 volts. And so let's say that 100 volts would destroy it. okay? And so we said that 10% of the components that would receive that, like some kind of an event would be destroyed. And the truth is that out of all of the out of all of the units that you had that were affected by that, essentially the other 90%, okay, so we're going to destroy 10%. The other 90% can be compromised by only 25 volts. So in other words, 1/4 of the voltage that will destroy those there, these units, only 1/4 of that much voltage is enough to compromise the rest of them. So honestly, what it comes down to is it's really sort of what they try to do is, in terms of protocols, is they really try to develop kind of a zero tolerance to static discharge, because anywhere that it appears, it really wreaks havoc with the components. And so what it comes down to is there's a few tips in terms of handling and setting up a safe area to actually work. And so I'm going to give you a few of the things that they do. First of all, components that are sensitive are typically always contained in anti-static packaging. Okay, so you're going to make sure that if they're being moved from one place to another, the components are actually placed inside of an anti-static container of some kind. And interestingly enough, you may have seen this, I've seen it before, somebody handling a printed circuit board, they pull it out, they know it's new, and they'll take it out and look at it, and they sort of have this feeling like, I should be careful with this. So they take the bag and they hold the board and they walk with it. And interesting thing is that the idea of the bag is to keep air from passing over the components, because it's the air passing by the components that creates the friction. So you actually want to keep it inside the anti-static bag, for a couple of reasons. So inside the anti-static is where it needs to be. Now, once a component is actually taken out, if you're actually working on it, there's several things that are important. First of all, if you're touching, if you're going to be touching the components, you need to be wearing a wristband. And the way that the wristbands work is that they go on, they make good contact with your with your skin, and they do normally have a lead that plugs into ground. And that lead will have typically a 1 megohm resistor in it, which will prevent you from getting a nasty shock if you actually happen to touch a live part in the circuit, because this wrist strap is going to be grounded. And so what you want is, you actually want everything around the components to be conductive. So you have a conductive workbench. And you have a conductive floor matting. And of course you have your wristband. And the other thing that you do, of course, is you remove items that are known to hold charge. So some things are worse than other things. Styrofoam packaging is horrendous for building up static charge. So what's the idea then behind the conductive workbench and the conductive floor mat? Well, what you want is you want equal potential. And so your conductive workbench is grounded, your floor mat is grounded, you're grounded, you're in contact with these things. And so whatever you do is, anytime before you touch any electronic component, you make sure that you first of all, you're connected to ground, but there's just a lot of attention paid to making sure that there's nothing around you. Even loose clothing is something that you don't want to have, because loose clothing against a chair, for instance, can build up a lot of static voltage. So they want to get rid of anything that can build it up, and at the same time, they're giving a conductive path for any charge to sort of bleed away without causing any kind of a discharge. And so, obviously, this is something that when it comes down to most of us, not something that's going to come up every day, but it is interesting to know how sensitive they can be, and secondly, some of the ideas that you can have to reduce the chance of causing damage to the components. Okay. Now, as I mentioned, I just want to summarize here the some of the most sensitive are the MOSFETs are high on the list. So VMOS and MOSFET, and they're very, very sensitive voltage levels as low as 30 volts. So we would say highly sensitive. And then as we move down, some of the least sensitive, and this is interesting to see as well, doesn't mean that they're not still sensitive, just much less sensitive. And these contain things like the BJT, uh, uh, basically regular rectifier diodes, the SCR, and the IGBT. So this is another one of the advantages of the IGBT, is that somehow throughout the way that it's constructed, it is less sensitive to ESD. So that's another factor that that is pretty positive for the use of the IGBT, insulated gate bipolar transistor. So that's where we're going to bring this session to an end. And like I said, please make sure you check into some of the examples, some of the work examples for the pulse width modulation, just to get familiar with that. And secondly, please make sure you take a look at the ESD information that I've included in the handout section.